All right, so we're going to start talking about rotational motion, and really the big thing about rotational motion is going to be comparing it to um, linear motion, and we're going to use equations to do that, obviously. So angular quantities. So in purely rotational motion, all these points, right, all points in this thing move in a circle, which we call O is our axis of rotation, which is just the center of the circle. The radius is R, probably learned that in math class. And then all points on a straight line drawn through the axis move through the same angle at the same time. So that's what we call the angle in radians. And you, again, something you probably did in pre-cal, but there's your angle in radians, okay? Which is essentially this, the arc length divided by the radius, okay? So here's your first equation. Angular displacement. So that's the change in angle. So that's going from this angle to, let's say, this angle. So this would be the change in angle, okay? So it's angle 2 minus angle 1. Angular velocity is change in angle over change in time. And then, I mean, the instantaneous angular velocity then would be the limit from t to 0 of the change in angle over change in time. But this is the big equation here. Angular velocity is change in angle over change in time. Angular acceleration is the rate at which the angular velocity changes over time. So angular acceleration, change in angular velocity, final minus initial over change in time. And again, instantaneous uses the limit. So linear velocity, so at every point on a rotating body has an angular velocity of W, then a linear velocity of V. Okay, so this is how they relate. So V is linear velocity. That's what we've been talking about since we started. How does it compare with angular velocity? If you take the radius of your rotation and multiply it by the angular velocity, you can find the linear or tangential velocity of your object. Big equation here too. So therefore, objects that are farther from the axis of rotation, so farther from the center, right, will move faster. So if we have an object here, both moving with the same angular velocity, the tangential velocity will be faster as you get farther away from the center, which should make sense mathematically and maybe makes sense theoretically, but here's the reason why, right? If the angular velocity changes, it has a tangential acceleration, all right? So tangential acceleration, and here's how it's evolved, is that if you take the radius times the angular acceleration, you can find the tangential acceleration, okay? Boys, a lot going on there that we could figure out then if we see something going in a circle. Even if the angular velocity is constant, each point of the object does have a centripetal acceleration. And again, acceleration is change in velocity, which means change in speed, or change in direction, which if you're going in a circle, always change in direction. So your centripetal acceleration, right? Right here, centripetal acceleration, angular velocity squared times your radius. Another equation, tons of equations here. So here's how linear and rotational quantities relate. Okay, displacement, linear, it's x, rotational, it's angle. Velocity, linear, it's v, here we got w. Acceleration, acceleration tangent, angular acceleration. And then here's the relationship, and this is big, okay? Big thing is, we've been doing degrees with our math. Everything goes radians now, so make sure you can adjust your calculators. But linear distance is equal to radius times your angle of displacement. Your velocity, your linear velocity is equal to your radius times your rotational velocity. And then your tangential acceleration is equal to the radius times your angular acceleration. So you can see radius, very important when we talk about circular motion. Another term that comes up that I wanted to address was frequency. Frequency is a number of revolutions per second. So it's a per second. We use hertz, which means per second, right? So frequency is angular velocity divided by 2 pi, which is a circle, right? Um, Another equation. And then if we want to find the time period for one revolution, we just take the inverse of the frequency. I'd say another equation, but that's something that should make sense based on units. But tons of equations will be on the board when we start talking about this. So let's do some examples. Bike wheel. A bike wheel rotates 4.50 revolutions. How many radians has it rotated? Do it now.
All right, so this first one mathematically isn't going to be too strenuous, but I wanted to show it to you anyway. So it says a bike wheel rotates 4.5 revolutions. How many radians has it rotated? So 4.5 revolutions. So we're going. So let's say we're in a circle, right? So 4.5 revolutions is what we're talking about here. Okay. Now here's what we know. One circle's a revolution. So one revolution is 2 pi radians. Okay. And this is a conversion, and this isn't a conversion that comes up a lot when we talk about revolutions, because a lot of times we'll count revolutions as opposed to counting radians when things are moving in circles. So converting from revolutions to radians will be something that you'll be asked to do quite a bit. And I want to make it as easy as possible for you. So if I have 4.5 revolutions, how many radians is it? Well, one revolution is 2 pi radians, right? So, calculator, if I take, I guess I don't need to calculate, I'll just keep things in terms of pi. If I take 4.5 times 2 pi, I get 9 pi radians. And so that would be my answer, okay? And then you'll have to, if they give you a measurement, you'll have to multiply 9 times pi and get your 27 and change to get there. But 9 pi radian is just fine. But just keep that in mind, as one revolution is 2 pi radian.
Birds of prey. A particular bird's eye can just distinguish objects that subtend an angle no smaller than 3 times 10 to the negative 4th radians. How many degrees is this? And how small an object can the bird just distinguish when flying at a height of 100 meters? Interesting problem. Do it now.
All right, so I tried to do my best representation of the bird and the prey. There's our angle, right? The angle that they talk about in radians, and then also this is L, the length. So how high above? I'm sorry, this is R, the radius. I'm gonna get that messed up, and this is my length, right? So how big the prey is the L. Okay, so that's the arc length, and that would be the radian. So this would be my circle going this way, okay? And I just want to see what this arc length would be with the radius r, all right? So first step is I have to convert radians to degrees, and it says it's 3 times 10 to the negative 4 radians, all right? So 3 times 10 to the negative 4 radians. So all the way around is 360 degrees, which means 2 pi is 360, so 2 pi radians is 360 degrees. So I calculate all this out. I get 3 exponent negative 4 times 360 divided by 2 pi. And I get 0.017 degrees. So that's my angle in degrees. And sometimes we want angles in degrees, sometimes we want to see them we want to see theta in degrees, or we want to see it in radians. But here's your conversion. 360 degrees is equal to 2 pi radians. And again, that will help with conversions, similar to what we talked about with the first one. All right, so that's our degrees. So now we know our angle, theta in degrees, and now we want to find L. And one of the equations that we gave is the arc length is equal to R times theta. And theta needs to be in radians for us to find arc length. So we just want to find our height. And our height, we said in R, is 100 meters. So L is equal to 100 times 3 times 10 to the negative 4. And that will give us our arc length that we're looking for. So again, we get the calculator out, and we get 100 times 3 exponent negative 4, and I get 0.03. My units are meters because that's meters. So that's also going to be the same as 3 centimeters. So our prey is 3 centimeters long. Okay, that's just using the equation of arc length, and then this is using 360 is equal to 2 pi.
Is the line faster than a horse? On a rotating carousel or merry-go-round, one child sits on a horse near the outer edge, and another child sits on a line halfway out from the center. Which child has the greatest linear velocity, and which child has the greater angular velocity? Do it now.
All right, so here's our lion, and here's our horse. So the horse is farther out in the path that it takes, right? And the lion is here, but we'll put them next to each other for sake of seeing that they're going to be near each other the whole time. So we talk about linear velocity. It's distance divided by time is linear velocity, right? In a straight line. So if I look at the distance L travels compared to the distance H travels a greater distance. So because H travels a greater distance in the same amount of time, H has greater linear velocity than L, okay? Greater distance over time is linear velocity. So the horse has greater linear velocity than the lion. But now we talk about angular. And the thing about angular velocity is that it's the angle of rotation divided by time interval. And since they both do one rotation, they both do 360 degrees over the same time interval. So 360 divided by time, 360 divided by time, which means angular velocity is going to be equal, even though linear velocity is not. And just thinking about that relationship, it's all based on the radius, right? The horse has a greater radius than the lion, therefore its linear velocity is greater.
A carousel is initially at rest. This is similar to the one we just did, but with numbers. At t equals 0, it is given a constant angular acceleration of 0.060 radians per second squared, which increases its angular velocity for 8 seconds. At t equals 8 seconds, determine the angular velocity of the carousel and the linear velocity of the child. And you can see the diagram down here, and we'll draw it again. And it's located 2.5 meters from the center point, so from our axis of rotation, right? And there's all the information. Do it now.
All right, so the diagram you saw on the problem, we're going in a circle, right? We accelerate the angular acceleration of 0.06 radians per second squared for 8 seconds. And we want to find what the linear velocity, or the angular velocity is going to be. In A, we want to find the angular velocity at that time. And then we also want to find the linear velocity, knowing that the radius of our circle is 2.5 meters, okay? So I'm going to add that there. So first off, we want to find the angular velocity. And we know that angular acceleration is equal to change in angular velocity over time. I know my angular acceleration. And then I also know that I start at, so my change is final minus initial over time, and my time is 8 seconds. 0.060 over 8. Final minus initial. My initials, I start at rest, is 0, so my finals all I'm going to solve for. And then I just solve for WF, which is going to be 0.06 times 8. And I get angular velocity of 0.48 radians per second. So now that's our angular velocity. Now we want to put it in linear velocity, and the equation that we used or that we showed you to use is V equals RW. So linear velocity is radius times angular velocity. So my radius is 2.5 meters. And my answer here is 0.48. That would be my linear velocity at that time. So if I take my answer from before and multiply it by 2.5, gives me a linear velocity of 1.2 meters per second. Make sure my units were good. And I use meters because that's meters. Again, just more conversions.
Angular and linear accelerations for a child on a rotating carousel from a before determine the tangential acceleration, so the linear acceleration, the centripetal acceleration, and the total acceleration. Good question. Do it now.
Okay, so same situation here, but now we're talking about the accelerations as opposed to the velocities. So we want to find the linear acceleration, which is the tangential acceleration if we're going in a circle, right? That's the acceleration that sends us off on a tangent if whatever we were on lost to friction and we had to go that way. Acceleration tangent is equal to radius times angular acceleration, right? So if I take 2.5 times 0.06, that would be my tangential acceleration. So 2.5 times 0.06, 0.15 meters per second squared. Now centripetal acceleration, as you recall from uniform circular motion, centripetal acceleration is v squared over r, and we figured out v, I'm going to look it up because I didn't write it down, from the previous problem, we figured it out to be 1.2, right? So our linear velocity is 1.2, divide that by our squared divided by our radius, and that will tell us our centripetal acceleration. So this is something that we've previously done, 1.2 squared divided by 2.5, 0.58 meters per second squared. So this is our centripetal, so that's the acceleration pulling us in, and then we have the tangential acceleration going this way. So now we want to solve for the actual acceleration or the total acceleration, which is just vector addition. So I'll do part C up here so I can have a little more room. But we have tangential going in the vertical, right? So I have vertical, and then I have my centripetal, which I'll say is going this way. And then this would be my total. So centripetal is going towards the center of the circle at, what did we say, it was 0.58. My tangential is 0.15. Okay, and then all I want to do is find the actual total. So Pythagorean Theorem, right? A total is equal to 0.58 squared plus 0.15 squared. Take the square root. So 0.58 squared plus 0.15 squared. And then I take the square root of that. And I get 0.60 meters per second squared, which is pretty close to this because this number is so much bigger than that. So my actual acceleration is 0.60. Now if I wanted to get a direction to that, I would just find theta, okay? And again, I could use, once I know this, I could use any of these. I'm going to use tangent, all right? So the tangent of theta is opposite over adjacent. Take the arctan of this. And you should get 14.5 degrees in degrees, and then you can convert it to radians if you needed to find it in radians. Remember, if go degrees, there's 360 degrees in 2 pi radians. So then I could convert that to radians if I wanted to, okay? I guess I'll do that while I'm sitting here, right? 14.5 times 2 divided by 360, 0.08 pi radians. That's what that would be.
And then in example 8.4, again, we found the carousel after 8 seconds rotates at an angular velocity of this, so we got the answer, and continues to do so after 8 seconds because the acceleration ceased. What are the frequency and period of the carousel when rotating at this constant angular velocity, which is 0.48 radians per second? Do it now.
All right, so we figured this as our angular velocity of 0.48 radians per second, and we want to convert that to frequency. Frequency is angular velocity divided by 2 pi. So I take 2.48 over 2 pi. And I get a frequency of 0.0. I want to have this in radians, don't I? Didn't have my calculator in radians. Let's try that again. 0.48 divided by 2 divided by pi. I get the same answer. I guess I was thinking angles. All right, 0.076, so we'll go 0.076 hertz. And then to go from frequency to period, right? If frequency is 1 over period, that means period is also 1 over frequency. So if I take the inverse of this, that should be my period. So 0.076, inverse button, my time period is 13 seconds approximately, some change. So that's how much time period it would take.